Okay, so hello, good evening. Welcome to week 6 of chemical applications of symmetry and group theory live interacting session. Okay, so what we have learned this week? So this week we have learned symmetry adapted linear combination and how we can use the projection operator or to get the what is the proper combination of atomic orbitals to get a particular symmetry adapted linear combination corresponding to a particular symmetric group of a molecule. Okay, so first we will go through some of the topics that we have already learned, and then we will solve some of the previous year assignments. Okay, okay, so let me just share my screen. Okay, so basically in this week we have learned first we have learned that what is the proper condition, like what is the proper condition of direct product to get a non-zero integration value, right? So the link between the quantum mechanics and the group theory. So in quantum mechanics, we have learned that time independent Schrodinger equation H psi equal to E psi, right? So this is time independent Schrodinger equation. Okay, now here H is the Hamiltonian, E is the energy eigenvalue, and psi is eigenfunction. Right, so this is an eigenvalue equation. Okay, now so to get the energy eigenvalue corresponding to a particular eigenfunction psi, what we will do, so to get the average energy, E average equal to some psi H psi d tau divided by psi star psi d tau. So this is the formula for average energy, right? Okay, you can where d tau is the volume element, this is the volume element, psi star is the complex conjugate of psi because psi is a complex function, right? So that's why psi star is the complex conjugate. H is the Hamiltonian operator. Okay, now to get the non-zero value of average energy, this psi star psi d tau has to be non-zero, like psi has to be normalized, and this integration, this psi star H psi d tau not is equal to 0, right? So this is the Hamiltonian operator. This is the Hamiltonian operator. So Hamiltonian operator is Hermitian. In general, it is a Hermitian operator, or it is the real symmetry, or it is a symmetric operator. Okay, it is symmetric. That means, so Hamiltonian is symmetric with respect to all symmetry operations. So basically, let's consider a molecule which belongs to a particular point group or symmetry group, and if you construct Hamiltonian corresponding to that molecule, then that Hamiltonian will be a symmetric. That means it will be symmetric with respect to all symmetry operations belonging to that particular point group. Okay. Now, so we have seen that each eigenfunction, this each eigenfunction can act as a basis for an irreducible representation. Okay. So each psi, this eigenfunction, can act as a basis for an irreducible representation. Now, what is the meaning of this integration? This integration, in the group theory language, you can say that, let's say, this psi act as a basis for an irreducible representation gamma A. Okay. Now H is a symmetric. Okay, and this psi can act as a irreducible representation corresponding to gamma B. Okay. Now, what is the meaning of this integration? This meaning of this integration in the group theory language, it will be, so gamma A direct product of H direct product of gamma P. Okay, this is the direct product. In group theory language. Okay. Now I've told that the H is symmetric for a particular point group. So H is symmetric with respect to all symmetry operations. Okay. Now this direct product has to have some totally symmetric representation. So in any point group, there is a totally symmetric representation, right, which we call A1 or A1G, like this. That means totally symmetric representation means all the characters of all the symmetry operations will be 1. Okay, that means that particular irreducible representation will be symmetric with respect to all symmetry operations belonging to that particular symmetry group. Okay, now this direct product, if we want to have a non-zero value of this direct product or of this integration, then this direct product in the group theory language has to have a totally symmetric representation. Okay, so it has to have totally symmetric representation. Okay, it has to have a totally symmetric representation. Why? Because let's consider a function where minus x2 plus x, y, or fx dx. Let's consider this integration. Okay, now let's consider the fx is an odd function. If fx is an odd function, then this integration, then minus x2 plus x fx dx will be equal to 0, right? Why? Because fx is an odd function. That means f of minus x will be minus of fx, right? That means if you change x to minus x, then the functional value will get negative sign. Okay, so f of minus x will be equal to minus of fx. That means fx is an odd function. That means when you are doing this integration, so integration means summing, right? So when you are doing this integration, then minus x to plus x, so minus x to 0 f of x dx will be what? So you can just split it up. It will be minus x to 0 fx dx plus 0 to x fx dx, right? So minus x to 0, when you put the value of x here in fx, then it will be minus of f of minus x, that would be just minus of fx, right? fx dx plus 0 to x, this will be fx dx. So this negative part will cancel out this positive part, okay? That means total integration value will be 0. That means when fx is an odd function, then f of minus x will be equal to minus of fx, then this integration value will be equal to 0. We'll don't have any non-zero value. So that means, so here fx is not symmetric with respect to the interchange of x to minus x, right? That means the inversion symmetry. So fx is not symmetric with respect to the inversion symmetry operations, because here you are changing x to minus x, then your functional value will get changed from f of minus x to minus of fx, okay? So it is not symmetric with respect to inversion symmetry. That means this function fx doesn't have a totally symmetric representation. That's why some positive part and the negative part will get cancel out each other, and total integration value will be 0. So to get a non-zero value of integration or non-zero value in group theory language, the direct product has to have some totally symmetric representation, okay? That means has to have some representation, irreducible representation, where all the characters will have value 1, and it's all the that means that particular representation will be symmetric with respect to all symmetry operations belonging to that particular point group. Now here H is symmetric. Now the direct product, the total direct product, if I want to get non-zero value, the gamma A and the gamma B direct product will have totally symmetric representation, right? That means gamma A and gamma B, gamma A and gamma B will be form a same irreducible representation. Then only the gamma A direct product gamma B will have a totally symmetric representation, okay? So basically the take home message is that if you want to get a non-zero value of this type of integration, then in the group theory language, the direct product between the three irreducible representation will have a totally symmetric representation. So here eigenfunctions can act as a basis for an irreducible representation. So let's say psi star is a basis for gamma A irreducible representation, psi is a basis for gamma B irreducible representation. So the total integration will be equal to direct product of gamma A, H and gamma B. H is symmetric. Now gamma A direct product of gamma B has to have some totally symmetric representation, and that is only possible only when gamma A and gamma B will be from a same irreducible representation, okay? And there is also an important integration for spectroscopic purpose. Okay, let me just check. Transition moment integral. Transition moment integral or TMI, okay? So let's say you have some energy state I, and you have some final energy state F. Okay, now you want to so you want to have some transition from the initial state I to initial state F. Okay, so the energy difference between these two states is, let's say, nu h nu if, where nu if will be equal to nu I minus nu f. Okay, this is the frequency difference or energy difference. So you want to just eradicate this initial state with some laser of energy difference, this h nu if. Then the molecule from the ground or from the initial state I will get will transit from I to F, right? And you will have some transition absorption. Okay, now to have successful transition or to have successful absorption process, the dipole moment of the molecule, the electrical dipole moment or the vibrational dipole moment, depending upon the transition type of transition, like electronic transition or vibrational transition, the dipole moment has to couple between these two states. Okay, has to couple these two states, initial states and the final state. Okay, because something has to couple the two state, or something has to mix these two states, initial state and the final state, so that the molecule can jump from the initial state to final state, right? So the transition moment integral is just like this. So the transition moment integral will be equal to psi f mu psi I. Okay, so this is the transition moment integral. That means here mu is the dipole moment operator which connects the initial state psi I to final state psi f. Okay, now the intensity of transition will depend upon the modular square of this transition moment integral. Psi square. Okay, so intensity of transition, so if you want to have high intensity transition, then this overlap integral or the transition moment integral value has to be large, or if this integral is 0, then you will not get any transition. Okay, so the condition of allowed transition will be non-zero value of this transition moment integral. Okay, now like we just we just saw psi f, or this is final eigenstate, this is initial eigenstate, and this is the dipole moment operator. So psi I will act as an basis for an irreducible representation, and psi f also will act as a basis for an irreducible representation, right? And for the electronic case, for the electronic transition, the dipole moment will be just charge time displacement. Okay, let's say charge is q, so q time x plus y plus z. Okay, so this will be the dipole moment operator. So if you want to have if you want to ask question is this transition x polarized or y polarized or z polarized, that means the transition is allowed only in the x direction, like if your electric field if you apply electric field along the x direction, then the transition will be allowed, or is it the y direction allowed or z direction? Okay, so then you have to compute the transition moment integral psi f. Let's say along the x direction the integration will be x, then psi I, right? So for a particular molecule, the molecule belongs to a particular point group or symmetry group, and there are some possible symmetry operations corresponding to that particular point group, and there are character tables, and there are irreducible representation, right? So psi I is an eigenfunction. Psi I will act as a basis for an irreducible representation, psi f also will act as a basis for an irreducible representation, and x will also act as a basis for an irreducible representation, right? So to have this non-zero value of transition moment integral, these integral values should have some non-zero value. Okay, now in the group theory language, it just means, let's say this is gamma a or gamma f, direct product of, let's say, gamma x and direct product of, let's say, gamma I. Okay, this group theory product or direct product has to have some totally symmetric representation. So the procedure is, step by step procedure is, first you have to identify the point group. Identify the point group the molecule belongs to. Then you have to write down the character table. Third, so you have to select, or you have to choose the which particular irreducible representation this each eigenfunction will act as a basis to. Okay, then you have to just you have to apply the group multiplication table, or you have to use the characters corresponding to that particular irreducible representation to solve this direct product. Okay, so direct product, basically gamma f times gamma x, basically direct product of two irreducible representation will be just the multiplication between the characters of two irreducible representations. Okay, now if the direct product will have some totally symmetric representation, that means a1g or a1 like this, then this transition moment integral will have some non-zero value, that means its value will be not is equal to 0, and then the transition will be allowed. Okay, and if the transition moment integral will have some 0 value, then the transition will be forbidden. Okay, so compute the direct product associated to the transition moment integral using character table. And if transition moment integral equal to 0, then the transition will be forbidden. And if TMI is not is equal to 0, then the transition will be allowed. Okay, so this is actually very important. So this is an important application of group theory. So using group theory, you can identify which particular transition will be allowed transition in spectroscopy, or which particular transition will be forbidden transition, or in which direction, like when we apply electric field along x direction, a particular transition can be forbidden, but when we apply electric field along the y direction, the particular transition will be allowed. Okay, it can possible, depending upon the direct product combination of different irreducible representation. Okay, so next we have studied SALC, or SALC is the symmetry adopted linear combination. Okay, so so using this term you can understand what the term is actually, what is the definition of this term. So symmetry adapted linear combination. So linear combination of what? Linear combination of different atomic orbitals. Like when you draw, or when you just draw the molecular orbital diagram. So how does the molecular orbital form? So molecular orbital forms from the from different combination of atomic orbitals, right? So atomic orbital has some symmetry. Or first you start with considering a molecule. So molecule belongs to a particular symmetry group or point group. There is a character table associated with the symmetry group or point group, and there are some irreducible representations, okay, which will be equal to the number of classes for a non-abelian group. Okay, now when you do the molecular orbital diagram, so molecular orbital, each molecular orbital forms from a combination of different atomic orbitals. Okay, and each atomic orbitals have some symmetry, and the combination of that atomic orbital, that means that particular molecular orbital will have some symmetry. Okay, so symmetry adapted linear combination means, so uh, you just strategically combine some of the atomic orbitals to form a molecular orbital which can act as a basis for a particular irreducible representation. Okay, this is what symmetry adapted linear combination means. Okay, or it is associated with the LCAO. This is another term which is the linear combination of atomic orbitals. Okay, so LCAO is the linear combination of atomic orbitals, and SALC is the symmetry adapted linear combination. So basically molecular orbital form using combination of different atomic orbitals, and number of molecular orbital will be number of atomic orbitals. Okay, so if you strategically combine some of the atomic orbitals, then you will get some molecular orbitals, and that particular each molecular orbital can act as a basis for an irreducible representation. Okay, so each molecular orbital can act as a basis for an irreducible representation. Okay, and number of molecular orbital will be equal to number of atomic orbital. Okay, now to know, you want to know what is the perfect combination, or what is the proper combination of atomic orbitals which give us a molecular orbital which represents or which can act as a basis for an corresponding irreducible representation. Okay, like you want to know the proper combination of atomic orbitals which give us our desired molecular orbital which can act as a basis for an irreducible representation. Okay, that is our goal. So here the projection operator will be helpful, can be helpful. So using the projection operator, we can identify from a combination of atomic orbital which particular combination will give us which molecular orbital corresponding to a particular irreducible representation. Okay, so our goal is to find out proper combination of atomic orbitals which forms a molecular orbital which is a basis for a particular irreducible representation. Okay, so here projection operator will be helpful. So we have learned about this projection operator in detail in our class, in our lecture videos. So what I will do, will solve some of the previous year assignments related to this projection operator. Okay. So consider an ethylene molecule. So basically what will this projection operator do? So projection, using the projection operator corresponding to a particular irreducible representation, we can find out the proper combination of atomic orbital which can act as a basis corresponding to that irreducible representation. Okay, that is the job of projection operator. Okay, so the first question says, so consider an ethylene molecule where point group is given. Point group is D2H. So taking CH bonds, CH sigma bonds as basis function, the irreducible components comes out to be Ag plus B1G plus B2U plus B3U. So what will be the cell corresponding to the B2U representation? Okay, so that in this question, the molecule is given ethylene molecule and the point group is also given D2H. So we have to take CH sigma bond. This is the atomic basis function. Okay, atomic orbital basis function. Each 4, so in the ethylene molecule 4 CH sigma bonds are there. So we have to take these 4 CH sigma bonds as basis function, and using these 4 CH sigma bonds, the irreducible components comes out to be Ag plus B1G plus B2U plus B3U. So we have to find out which particular combination of this 4 CH sigma bond will give a molecular orbital which can act as a basis for the B2U representation. Okay, so using the projection operator technique we can find out easily. Okay, so what is the procedure? So first, ethylene molecule, that means C double bond C, H, 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 H. So this is ethylene molecule and it is D2H point group. Okay, so first we have to write down the D2H character table or the possible symmetry operations associated with the D2H point group. Okay, so here 4 sigmas are, this is sigma 1, or sigma 1, sigma 2, sigma 3, sigma 4. These are the 4 sigmas. Okay, sigma 1, sigma 2, sigma 3, sigma 4. These are the basis functions. Okay, now we have to write down the first D2H character table. Okay, what is the character table of D2H? So the possible symmetry operations for the D2H are E, C2Z, C2Y, C2X, I, sigma XY, sigma XZ, sigma YZ. Okay, so number of classes is 1, 2, 3, 4, 5, 6, 7, 8. So total 8 classes. So number of irreducible representation will be 8. So what will be the characters? 1, 1, 1, 1, 1, 1, 1, 1. This is the totally symmetric representation. Then so basically like this there will be 8 irreducible representation. So this is AG. Okay, then there will be B1G, B2G, B3G, AU, A1U, B1U, B2U, B3U. Okay, 8 irreducible representation. Now using this 4 sigma as basis function, what is the reducible representation? Okay, so to find out the characters corresponding to the reducible representation, so what we will do, so the short procedure is we have to find out the which particular sigma or which particular basis under some symmetry operations will alter their position. Okay, so if a particular basis or particular function alter their position under some symmetry operation, then that particular basis will not contribute to the diagonal term. Okay, so that particular basis will not contribute to the character corresponding to the reducible representation. And if some function or some basis doesn't alter their position under some symmetry operation, then that particular basis will contribute to the diagonal term corresponding to the matrix representation of that symmetry operation. So it will contribute to the character of that particular symmetry operations corresponding to the reducible representation. Okay, so here reducible representation, to find out the reducible representation, so basically, so if you draw this C double bond C, sigma 1, sigma 2, sigma 3, sigma 4, right? So with E operation, so E C2Z, C2Y, C2X, I sigma XY, sigma XZ, sigma YZ, right? So if you perform identity operation on this 4 basis function, then the 4 basis function will not alter their position. So the all 4 basis function will contribute to the character or to the diagonal. So diagonal term will be, so the total character will be 4, right? Like this. So 1 1 1 1. So the trace is the character, so trace will be 4. Okay, then next operation C2Z. So C2Z is like this. So this is like Z, this is X, and this is Y. Okay, that means XY is the plane, molecular plane, and Z is the above the plane. So if you perform 180 degree rotation around the Z axis, above the plane around the Z axis, then C4 comes here, like sorry, C4 means sigma 4 comes here, sigma 2 will become sigma 2, sigma 2 will go there, then sigma 2 will go sigma 4, then sigma 1 becomes sigma 3, and sigma 3 becomes sigma 1, right? So all 4 positions, all 4 sigma bonds are altering their position under the C2Z symmetry operations. That means the contribution from this all 4 sigma to the diagonal will be 0 0 0 0, right? That means total character will be 0, like this. So it will be 0 0 0. Now sigma y, sigma xy means it is the horizontal plane, molecular plane, the plane reflection with respect to this molecular plane. So with respect to this molecular plane, all 4 sigmas will not alter their position, right? So the total character will be 4 and 0 0. So this is the irreducible representation. Okay, now if you just compute that which particular, what is the contribution of each irreducible representation to this reducible representation, then you will get this particular combination AG plus B1G plus B2U plus B3U. You can compute like this, right? Because we have seen the formula. What is the formula for each contribution of each irreducible representation to any reducible representation, right? So let's say this is gamma reducible, gamma R, okay, or capital gamma. So and this is, let's say, gamma I, okay. So the contribution of each gamma I, AI will be equal to Li by H. Li is the dimension. Li is the dimension of that particular irreducible representation. H is the total order of the group. Then sum of R. R is the symmetry operation. Then character of gamma. Then character of gamma I. Okay. So this is the formula for to compute the contribution of each irreducible representation to a particular reducible representation. Okay, so if you just do this, and you will get reducible representation gamma will be composed of AG plus B1G plus B2U plus B3U. AG plus B1G plus B2U plus B3U. You will get this combination. Okay, so this is reducible representation okay, and these are irreducible representation. Okay, now we have to find out what is the proper SALC, or for what is the proper combination of these 4 basis function for the B2U representation. Okay, so using the projection operator technique. So projection operator so the short from, so there are two types of projection operator: complete projection operator or incomplete projection operator. So complete projection operator, you will compute by term, diagonal term by term basis, like 1 1 2 2 3 3, like this. Or in incomplete projection operator, you use the characters corresponding to that particular symmetry operations. Okay, so like for the in so incomplete projection operator, so let's say P of some irreducible representation, let's say B2U. Okay, then you will operate just one basis function here, sigma 1. Okay, then so what you have to do, the formula will be Li, which is the dimension of that irreducible representation here, B2U. Okay, then divided by H, where H is the order. Okay, then it will be character of B2U representation, or it will be summation of R character of B2U. Here we are using B2U, that's why I am using B2U here, B2U representation for each symmetry operations. Okay, then times multiplied by what this basis function will alter to, okay, under this particular symmetry operation. Okay, then sigma 1 R, this is the formula. So this is the formula just. So for P projection operator B2U, so if I operate on sigma 1, then it will be, so first symmetry operation is E2, then C2Z, C4, C2Y, C2X, like this. Okay, so what I have to do, so first character of E is 1 times this sigma 1 under operation E. Okay, so under identity operation, sigma 1 will be sigma 1, right? So times sigma 1, then plus, then the character of C2Z, character of C2Z under B2U representation. Okay, so character of C2Z under B2U representation, it will be minus 1 times sigma 1 under C2Z representation. So what it will do, so this is sigma 1 and C2Z is above the plane Z axis, 180-degree rotation around the Z axis. So sigma 1 will go from here to here, sigma 1 will transform to sigma 3, right? So under C2Z representation, C2Z symmetry operation, sigma 1 will transform to sigma 3, like this. Then C2Y operation, the character of C2Y operation under B2U representation, so character of C2Y under B2U representation, it will be 1. then sigma 1 under C2y. So what will it be? C2y, so this is y on the plane, this is y. So if you perform sigma y, C2y, the 180 degree rotation around this axis, then sigma 1 will become sigma 4, right? So like this, then sigma 4, then like this, if you then minus 1 times sigma 2, then plus 1 times minus 1 times sigma 3 plus 1 times sigma 1 plus minus 1 times sigma 2 plus, then last symmetry operation is sigma yz. So sigma yz, sigma 1, so if you sigma 1 is this, and if yz means this is y and z is above the plane, so yz sigma 1 will become sigma 4. Okay, this is easy. So 1 times sigma 4. So if you just solve this, you will get sigma 1 minus sigma 2 minus sigma 3 minus sigma 4. So this particular combination you will get. Okay, what does this mean? This means, so these 4 sigma 1, sigma 2, sigma 3, sigma 4 are acting as bases to form molecular orbital. Now we have to find out proper symmetry adapted linear combination of these 4 sigmas corresponding to the B2U representation. So we are using the projection operator technique here. So the projection operator technique, so P is the projection operator under B2U representation. If I operate this on a particular sigma or particular basis, sigma 1, the formula will be character of that particular B2U representation and corresponding to a particular symmetry operation times this sigma 1 or this basis. What basis, what particular basis you will use? You can use sigma 1, sigma 2, sigma 3, sigma 4, any of this. So this means sigma 1 under symmetry, under a particular symmetry operation. Okay, so in reality this means, so projection operator under irreducible representation B2U, you are operating this on a basis function sigma 1, then you are just multiplying character of that B2U representation under a particular symmetry operation times sigma 1 under that particular symmetry operation. Okay, then you are getting a combination sigma 1 minus sigma 2 minus sigma 3 minus sigma 4. That means this particular combination is a molecular orbital, and it is now not normalized. You have to normalize it. So this particular combination is a SALC or symmetry adapted linear combination corresponding to the B2U representation. This is the functional form. So if you just normalize it, then after normalizing it, this function can act as a basis for the B2U irreducible representation. Okay, so the answer will be, so SALC for B2U representation will be sigma 1 minus sigma 2 minus sigma 3 minus sigma 4, this combination. Okay, this functional form. So like this, you can get any combination of these four sigma 1, sigma 2, sigma 3, sigma 4 to form a molecular orbital for any irreducible representation. Okay, using the projection operator, you can get the functional form easily. So then the next question is, so using this you can so for any point group or any molecule you can form symmetry adapter linear combination. You can find out the symmetry adapter linear combination for any irreducible representation. Okay, for two-dimensional representation, so you have to apply 2 times. Okay, and in this case has been discussed in the lecture videos. Okay, so next I will discuss the Huckel approximation. And secular equation. Okay, so what is secular equation? So let's consider a molecular orbital psi. So this is a molecular orbital which we can get from the linear combination, proper symmetry adapter linear combination of atomic orbitals. Okay, so it will be sum of I Ci phi I, where Ci is the coefficient. Okay, and phi I is the atomic orbital. So phi I are normalized. Okay, so now this psi is the molecular orbital. So if we use two atomic orbital, then you will get two molecular orbital. Okay, so let's say psi will be basically C1 phi 1 plus C2 phi 2, and the C1 and C2, the values of C1 and C2 you can compute using the secular determinant by solving the secular determinant. Okay, now what is the time independent Schrodinger equation? Time independent Schrodinger equation will be H psi equal to E psi. That means you'll get H minus E psi will be equal to 0. Okay, so then you can just put this H minus psi Ci phi I will be equal to 0, right? So if you just break this term, it will be C1 H phi 1. So basically it will be C1 H minus, this is E phi 1 plus C2 H minus E phi 2, it will be equal to 0. Okay, now if we multiply phi 2 both side, then integrating, so you will get C1 phi 2 H minus E phi 1 plus C2 phi 2 H minus E phi 2 will be equal to 0. So you will get term like this: C1 phi 2 H phi 1, this is d tau, this is d tau, d tau minus phi 2 E phi 1 d tau plus C2 phi 2 H phi 2 d tau minus phi 2 E phi 2 d tau equal to 0. So now each individual term let's analyze. So it is, you are getting term like this: phi 2 H phi 1 d tau. So what does this mean? So this is Hamiltonian operator, and this is phi 2 and this is phi 1. Okay, so this is the average energy or interaction energy between phi 1 and phi 2. Okay, so now we call this term H21. Okay, now another term will be phi 2 E phi 1 d tau. So E's energy is constant, so you can take it out. So E phi 2 phi 1 d tau. So this is kind of like overlap integral. So phi 2 times phi 1 d tau. Okay, that means two functions are kind of so you are just multiplying two functions and integrating. That means you are just wanting to find out how much these two functions are getting overlapped with each other. So this is the overlap integral, and we call this S12. Okay, so from this you will get C1 H21 C1 H21 minus ES21 plus C2 H22. Then this phi 1 phi 2, this phi 1 phi 1 d tau equal to phi 2 phi 2 d tau. So this is like S11 equal to S22 will be equal to 1. So this is the overlap integral normalization condition, it will be 1. Okay, so H22 minus E will be equal to 0. Okay, so this is one equation you will get, and if you multiply this term with phi 1, and if you just integrate, so here you are just multiplying phi 2 and integrating, and if you multiply with phi 1 and then integrating, you will get another equation. Okay, so it will be like c1 h11 minus e plus c2 h12 minus es12 will be equal to 0. These two equation you will get, and from these two equation you can get the value of c1 and c2. Okay, then you can put the c1 value of c1 c2 here, and you will get two molecular orbitals. Okay, like this. So by solving secular equation, you will get the particular functional form of the molecular orbital. Okay, so here you will get some matrix equation. Okay, so it will be like h11 minus e, then h12 minus es12, then h21 minus es21, h22 minus e. This matrix equation you will get. Okay, so this linear equation, this two linear equation means you have to solve this matrix equation. Okay, okay, then if you solve this matrix, if you solve this matrix, then you will get two energy value, E1 and E2. So these two energy values are the eigenvalues. So okay, one corresponding to one molecular orbital psi 1, another corresponding to another molecular orbital psi 2. So by solving this secular equation, you can get the energy value corresponding to that two particular molecular orbital. Okay, now like this. So when you do the molecular orbital diagram from low energy to high energy, you are solving the secular equation. From this secular determinant, you are getting the energy eigenvalue, then you are just putting the energy value corresponding to that particular molecular orbital. Okay, from low energy to high energy. So by solving this, you will get two energy eigenvalue. E1 and E2. Okay, now so here I am just using simplest example, like I am using two atomic orbital which are combining to give two molecular orbital. So that's why the dimension of the secular determinant is 2 cross 2, right? So if I use, or if I use 10 molecular orbital or 10 atomic orbital or 20 atomic orbital to form a molecular orbital, then from 10 atomic orbitals I will get 10 molecular orbitals, right? So our the secular determinant size of the secular determinant will be what? 10 cross 10, right? So to solve this 10, so we have to solve this 10 cross 10 determinant to get the 10 energy eigenvalue corresponding to 10 molecular orbital. Then from low energy to high energy, we can fill the molecular orbital with electrons. Okay, like this. So this is the basic concept. Now here, so basically, so here our secular determinant, like 2 cross 2 secular determinant. So if I can get, if by some assumption all the off diagonal terms will be 0, or we can make it sparse, if we can make this matrix sparse, then it will be easily solvable. Okay, for higher dimensional matrix, if we can make some matrix element 0 or make the matrix sparse, then we can easily solve the matrix. So here comes the Huckel approximation. Okay, so Huckel approximation. So Huckel says, so like H11, that means that integration of phi 1 times phi 1 times d tau, like this type of matrix, like in general HII or IJ, when phi I phi j d tau when I equal to j. This type of elements is the energy of the H. This is the energy of the phi I atomic orbital, okay, and this will be denoted by alpha I, okay. So this is the energy of the phi I atomic orbital, okay. Now another case will be Hij, which will be phi I H phi j d tau when I not is equal to j, then it will be just interaction energy, okay. So interaction energy between phi I and phi j, okay, and this will be denoted as beta ij, and this is called resonance energy. Resonance energy generally is negative, it is the stabilizing energy, okay. So Huckel, and the another term will be like this phi I phi j d tau will be S ij will be 1 when I equal to j, and will be 0 when I not is equal to j, okay. So this is the Huckel's approximation. So Huckel approximation Huckel approximation is, so when let's say this is I, okay, so this is let's say 1 2 3 4 5, these are the atomic orbitals, okay. Now when if two atomic orbitals are adjacent to each other, let's say 1 2 2 3 or 3 4 like this, or 4 5, if two atomic orbitals are adjacent to each other, then their interaction energy Hij will be equal to beta ij, okay, if I and j are adjacent, and if not, then Ij equal to Hij equal to 0 if not adjacent. So this is kind of assumption. If two atomic orbitals are adjacent to each other, then their interaction energy will be beta ij, or if two atomic orbitals are not adjacent to each other, then their interaction energy will be equal to 0. So H12 will have beta 12, H23 will be beta 23, but H13 will be 0. H24 will be 0 because these 2 and 4 are not adjacent to each other, okay. And for overlap integral, if is I equal to j, then it will be 1, if not I not is equal to j, then it will be 0, okay. So this is the Huckel's approximation. like this. So there are some questions related to this. So under Huckel's approximation, so basically Hij equal to beta when, so we just seen Hij will be equal to beta when I and j will be adjacent to each other, right? Otherwise Hij will be equal to 0 when I and j will be adjacent to each other. Then next question is under Huckel approximation, Hij equal to alpha when, so Hij will be equal to alpha when I equal to j. Okay, that means it is the self energy, like energy of the atomic orbital I. When I will be equal to j, then Hij will be equal to alpha. Okay, like this. So next, okay, so our last topic for this week is vibrational degrees of freedom. Okay, so let's consider a molecule. So molecule have, let's say, A, B5. Okay, so let's say molecule has total 6 atoms, right? And it is a non-linear molecule. Okay, now so basically if a molecule has n atoms, then for each atoms there will be 3 degrees of freedom, like 3 Cartesian coordinate at least minimum. So for each atom there will be 3 degrees of freedom. So for n atom it will be 3n degrees of freedom, right? So out of these 3n degrees of freedom, so 3n degrees of freedom will be composed of key translational, rotational and vibrational, right? Okay, so translational, so for a particular molecule, let's say this is a molecule. Okay, this is a molecule and this is a non-linear molecule, and for translational means translate. Okay, translation, it can go along x direction, along y direction, or along z direction, right? So 3 independent direction it can translate. So there will be 3 translational degrees of freedom. And if it is a rotational non-linear molecule, then there will be 3 rotational degrees of freedom. Or if it is a linear molecule, then there will be 2 rotational degrees of freedom. Because for non-linear molecule, because if you consider this molecule, you can rotate along y, along z, and along x. So there will be 3 independent rotational degrees of freedom. But if it is a linear molecule, then this along this axis, molecular axis, there will not be any rotation, right? Because if you rotate, then the molecule will be indistinguishable. Okay, so the independent rotational degrees of freedom will be 2. So the rest will be vibrational degrees of freedom. Okay, rest means out of 3n, out of these 3n degrees of freedom, 3 will be translational, 3 will be rotational for nonlinear, and 2 will be rotational for linear molecule. And out of this 3n, the rest will be vibrational degrees of freedom. So 3n minus 6 for nonlinear and 3n minus 5 for linear. Okay, this will be vibrational degrees of freedom. So there are some questions. So how many vibrational degrees of freedom for PF5 molecule? Vibrational degrees of freedom for PF5 molecule. Okay, so PF5, total number of atoms n equal to 1 plus 5 equal to 6. So total degrees of freedom 3n will be 3 times 6 equal to 18. Okay, and PF5 is a nonlinear molecule. So vibrational degrees of freedom will be what? 3n minus 6. So 3n minus 6, so 18 minus 6 will be 12. Okay, so this will be the answer. Pretty easy, right? For SF6 also, for SF6 number of, so for SF6 total number of atoms n will be 1 plus 6 equal to 7. So 3n will be equal to 21, and it is also a nonlinear molecule. So vibrational degrees of freedom will be 3n minus 6. So 3 times 7 minus 6, 21 minus 6, 21 minus 6 will be equal to 15. For SF6 there will be 15 vibrational degrees of freedom. Okay, so like this, if you can compute for how many vibrational degrees of freedom for nonlinear molecule and for linear molecule. For nonlinear molecule it is 3n minus 6, and for linear molecule it is 3n minus 5, where n is the number of atoms, total number of atoms. Okay, so like this. So all the other questions you can solve easily by just following this procedure. Okay, okay, so see you in the next week. Thanks much.